Okay, well, this is a video lecture for Chapter 12, looking at how to size um, fan fans and ducts for an all-air system. So we're going to be looking at several things. We're going to be looking at, first of all, fan characteristics, which is similar to the characteristic curves that we looked at for pumps. We're going to be looking at fan laws performance, which is an equivalent to the affinity laws we learned for piping networks. We're going to be looking at how to size ducts using two methods. One is called the equivalent length method, and another one is called the loss coefficient method. So basically, we'll be looking at ways to size duct systems and fans associated with it. To start off, I would first look at how to look at fan work. So for fans, you get that the work is going to be, the work rate I should say, is going to basically be the integrated, the mass flow rate times the integral of the specific volume over pressure. This is all based on thermodynamics. In this case, we can look, this basically sums up to flow rate times change in pressure. When we're looking at the pressure for air systems, pressure in this case is going to be measured in units of inches of water. The pressure drop is much less than that than in piping networks. Piping networks, we look at feet of water or head, and when we're looking in HVAC systems, all air systems, your total pressure drop will be measured in terms of inches of water. So if you want to get, if you're looking at flow rate, or I'm sorry, if you're looking at pressure in inches of water, usually the flow rate is in CFM, flow rate of air, and then the W sub S is going to be what we're looking at in terms of shaft work. So the shaft work is going to be the obviously the work from the armature or the shaft of the fan, and that'll be in terms of horsepower. So basically, to get work, we're looking at two work: static work and total work. But the work is going to be in terms of where Q dot is in CFM, pressure is in terms of PS in inches of water, and then you divide that by 6350 in order to get the work in horsepower. So you're looking at two different types of work. We're going to look at static work. Static work is going to be associated with what's called the static pressure. And then we also have total work, which is going to be, again, flow rate times total pressure. Okay, so if you're looking at efficiency, the total efficiency is going to be the total work that you get out of the fan over the shaft work, and the static efficiency is going to end up being the static work over the shaft work. So the shaft work is again the power from the fan shaft, and then you're going to have two types of work. You're going to have static work and total work, which gives you the amount of work necessary to overcome the static pressure, and then the total work is the work necessary to overcome the static pressure and also induce a velocity. Just to kind of go over the difference here in terms of velocity and static, we have something called velocity pressure. Total pressure is going to be static pressure plus this velocity pressure. Velocity pressure is rho times velocity divided by 2g. So if you want to get that in terms of unit, I want to try to get this equation, rho v squared over 2g, in terms of units that we're going to be using. So if you look at it this way, you get, if you take the density of air, 0.0765 pounds per square feet. And then here, if you want to end up with velocity in feet per minute, convert it from seconds. And then you want to get your pressure in terms of inches of water. There's 12 inches of water. We'll throw in 12 inches of H2O divided by 62.4 pounds per square feet, or per cubic foot, which is the density of water. And then that divided by gravity. So this should be able to go ahead and get your velocity pressure by basically being able to plug in velocity in feet per minute. So if you take that velocity feet per minute divided by 4,005 and square it, that should get you your velocity pressure. So all I did was go ahead and try to get a term for velocity pressure, throwing in a bunch of conversions in there in order to be able to throw in the velocity in feet per minute, and then to get outputted the pressure in terms of inches of water. Okay? So let's bring that all together in an example problem. This is problem 12.1 from your book, and it reads, a centrifugal fan is delivering 1700 CFM of air at a total pressure differential across the fan of 1.4 inches of water. The fan has an outlet area of 0.71 feet squared and requires 0.7 horsepower of shaft input. Compute the total power, the static efficiency, and the total efficiency, as well as the fan static pressure. So this problem is telling us that we have a flow rate of air of 1700 CFM. It's telling us that the total pressure differential across the fan, the total pressure differential is 1.4 inches of water, and the area that basically that the fan moves at, or that the fan covers, is 0.71 square feet, and the shaft work is 0.7 horsepower. So part A is asking us to compute the total power. Pulling the equation from a few prior slides, you can get that total power is going to be flow rate in CFM multiplied by delta T divided by 6350. So it's basically just a plug and chug in terms of the givens from this problem. You plug in the total work, you get 0.375 horsepower. Part B is asking for the static efficiency. So the static efficiency is going to be the static work over the shaft work, where a few slides earlier we looked at static work as being flow rate times the static pressure, that again divided by 6350. So what happens is that now that you have actually given to you the total pressure, and you need to figure out what the static pressure is. Knowing the total pressure, you can actually subtract out the velocity pressure. So the total pressure is static plus velocity pressure. So the static pressure would be the total minus velocity pressure. I don't know what my velocity pressure is, but I can compute that as velocity in feet per minute divided by 4,005 squared. So knowing my flow rate of 1700 CFM and knowing my area is 0.71, I can pull pretty quickly from that what my velocity is. So it should be flow divided by area. So if I get my flow rate 1700 CFM divided by my area 0.71 cubic square feet, I should get that my fluid velocity is about 2400 feet per minute. I plug that into my velocity pressure, and I should end up with a velocity pressure of 0.537 inches of water. I can use that in order to get my my static work. I'm sorry, I have to get my static pressure. So now, knowing that, I can go to the next slide here and get my total static pressure again, which is going to be the total pressure 1.4 minus the velocity pressure 0.357, and I get my static pressure of about 1 inch of water. From there, I can get my static work. So my flow rate times my static pressure divided by 6350, that gives me about 0.28 horsepower. And from there, I can get my static efficiency, which is static work over shaft work, which is given to me in the problem, stat to shaft work. 40% static efficiency, total efficiency, which is total work, 0.375 over 0.7, which is shaft work. 54% total efficiency, 40% static efficiency. I'm going to stop there in that problem. So basically this problem was just to be able to get you to learn how to use the equations associated with a fan. So you have static pressure, which is the pressure that the fan needs to produce in order to overcome, in order just to start the fluid flowing. Then you have the velocity pressure, which is the pressure above static pressure that gets the fluid velocity to flow. Let's try another example problem. This one's a little different. This one is this example problem takes a look at a table from your book. So table I believe it's 12.2a. The problem reads is that a small system requires 0.88 inches of total pressure, 0.88 inches of water of total pressure at a flow rate of 1420 CFM. Just remember, some people get confused about why are you using inches of water for pressure measurement, because that's what's used in the field. It's the pressure is too small to use feet of water, so they use inches of water. So a small system requires 0.88 inches of total water pressure at a flow rate of 1420 CFM. Select a suitable fan using the data in the table below. And then it says to sketch the system and fan characteristics looking at the operating point. So we're going to go ahead and do that as well. And what is the fan and total power, the fan speed and total power? So basically it's looking, again, it's saying that we have 0.88 inches of total pressure. And here what we're given, if you look at the notation here, down here it's saying that according to the subscript here, A, that this is actually static pressure. So here we have a 1/2 inch, 5/8 inch, 3/4 inch, 1 inch, 1 1/4, and 1 1/2 inch of static pressure. This column right here gives us the total flow rate. So we have volume flow rate, increasing volume flow rate, the associated outlet velocity for this particular fan for each of those flow rates. So basically a volume flow rate of 851 CFM gives us a outlet velocity of 1200 feet per minute. And then if you look over here for the different static excuse me, for the different static velocity, static pressures, here we have a certain amount of RPM that's needed in order to overcome the static pressure. So we have RPM and then the associated power for that particular RPM speed. So here, for example, we're going to look at 1560 CFM. We would need 2200. We would end up with 2200 feet per minute of outlet velocity. If we have a 1/2 inch of static pressure, we would need to rotate this at 1096 RPM. If there was 5/8 inch of static pressure, we would need 1147 RPM, and so forth and so on. So according to this problem statement, it is saying that we have a flow rate of 1420 CFM. The closest flow rate that we have here, the 1420 CFM, is 1418. So that's going to be the point that we look at, is 1418 CFM. So from that table, which from that table, you should be able to pull some values. Now, I'm actually in the process right now of opening up the book to confirm what the table is in the book, because that could have been from an earlier edition. The example problem that I had is from an earlier edition. So just to make sure that we're on the same page, I am in the process of opening up the book right now to confirm which table that is equivalent to. That would be the equivalent to table 12.1a in your book. So this would be from table 12.1a, which is basically the equivalent of this. So this in your edition is table 12.1a. So if you look at table 12.1a, if you select If you select 1418 CFM, why am I picking 1418? Because if you look at the problem statement, it's saying that, hey, I have a total water pressure of 0.88 inches of water at a flow rate of 1420 CFM. I don't have 1420 here listed in this chart. All right, but I do have, the closest thing I do have is 1418. So this is going to be my operating point right here. 1418 CFM for 2,000 feet per minute worth of flow, fluid velocity. And then it's telling me that I have a total of 0.88 inches of water total pressure. So I'm going to select 1418 CFM, which according to the table gives me a velocity of 2,000 feet per minute. So first thing I'm going to do is go ahead and find my corresponding velocity pressure. What this will help me to do is define what my static pressure is, right? So if I have a total pressure of 0.88 inches of water, how do I know what my static pressure is? Which static pressure column do I pick? Well, that's going to depend on the flow rate. That's going to depend on the fluid velocity. So my fluid velocity in this case is 2,000 feet per minute. So again, pulling the equation from earlier, velocity in feet per minute divided by 4,005, I square that, I end up with 2.5 inches of water as my velocity pressure. Total pressure is static plus velocity. So if I want to actually calculate my static, I need to take my total pressure and subtract the velocity pressure. So in this case, in the problem statement, I have 0.88 inches of total pressure minus 0.25 inches of velocity pressure. My static pressure ends up becoming 0.63 inches of water. And if I go back to the table, this is approximately 5/8 of an inch of water. So if I go back here, I'm going to go ahead and erase this. Looks like I'm landing on this column, which is 5/8 of an inch. So from that, if I look at 5/8 of an inch static pressure, it looks like this is my operating point. Looks like I have about 1,092 RPM. So this is asking for the fan speed. That fan speed would be 1,092 RPM, and my power is 0.39 horsepower. So that would be the power associated with it. So here from the table, add a static pressure a 5/8 of an inch of water, I get my fan speed as 1092 RPM with a total shaft power of 0.39 horsepower. Okay, so that's basically how I would pick the appropriate fan speed based on my total pressure, velocity pressure, and static pressure. Okay, so the next part of the problem, if you remember, the next part of the problem was asking, well, part of the problem too was looking at the system characteristic. Sketch the system and fan characteristic. How do I go about doing this? Well, if I look at the fan characteristic, well, I can go ahead and try to use those charts to basically do the same, to pull different operating points. What do I mean by that? So if I go back here and I look at my different fan speeds, let's say I keep the fan speed constant. All right, I'm going to keep the fan. Let me rewind a little bit. This comes back to affinity laws. Okay, the affinity laws for fans is the same more or less as it was for pumps. Basically, that the ratio of the new pressure over the old pressure is equal to the old RPM speed over the new RPM speed squared. Right? So the new shaft work or power over the old is equal to the new power or new RPM speed over the old RPM speed cubed, and the new flow rate over the old flow rate is equal to the old speed over the new speed to the first power. So basically the ratio of the old to the new flow rate is equal to the ratio of the old speed to the new speed. The new speed to the old speed, sorry. So using these affinity laws, I can go back to that fan and trace what would be called the fan characteristic. I can trace the fan characteristic for constant. So again, I know that this is kind of hard to keep paying attention in the video. But what we're going to try to do is look at the fan's characteristics. So basically, if I were to keep the fan speed the same, what would the changing flow rates look like? So let me go back here to the chart. I have here a speed of 1092. Let's vary the static pressure. Again, the total pressure is still going to be 0.88. But if I decrease my static pressure, let's say to, I don't know, let's decrease it to a half an inch here. I said increase, let's decrease it half an inch. So if I go here, I'm going to try to find the speed, the RPM speed that's closest to 1092. That would be here at this operating point. So if I were to decrease the fans, or keep the fan speed the same, but let's say that I increase my flow rate. If I increase my flow rate to 1560 CFM, I end up with a face velocity of 2200 feet per minute. Still at the same RPM speed, but with a different static pressure. Right? So, if I were to pull those numbers, again, this is from the table. In this case, I'm going to go ahead and say at an RPM speed of 1096, I get a velocity of 2200 feet per minute and a flow rate of 1560 CFM for a static pressure of 1/2 inch of water. Right? In this case, my velocity pressure, velocity over 4,005 squared, is equal to 0.3 inches of water. My total pressure is still within the 0.88 inches of water, which is what I have as a total. So what I'm looking at are different operating points. Again, keeping the RPM speed the same. Let's try another one. What if I were to go to increase my static pressure to 3/4 of an inch, and my RPM speed's the same? Here I would have 1078. That's about the closest that I can find to 1092. That would give me, again, different fluid velocities and flow rates. So sorry, as I say 10, I meant 1078. That's why I was silent for a minute. Sorry, guys. So 1072, the closest fluid, the RPM speed here would be 1078. So that'll land me right here. So that'll give me a fluid velocity of 1700 CFM and a flow rate of 1205. So for keeping the fan speed as constant as I can, 1078, in this case I would get 1700 feet per minute for a flow rate of 1705 CFM. That's all with a static pressure of 3/4 of an inch of water. If I were to find my velocity pressure, my velocity pressure in this case would be 0.18 inches of water, which gives me a total pressure of about 0.93 inches of water. So that gives me 3 operating points with 3 different static pressures. So my characteristic for this would look like the following. Pressure on the y-axis, flow rate on the x. I'm going to look at 3 operating points. 1, 2, and 3. All this for an approximate RPM speed of 1096 RPM. I would have here, this would correspond to 1200 CFM. This would correspond to 1420 CFM. This would correspond to 1560 CFM. I have here my total pressure of 0.93 at 1200 CFM, and then static pressure of 0.75. Again, the difference between these two would be the velocity pressure, because that would be total pressure and that would be static pressure. And then at 1420 CFM, my total pressure is 0.88. My static pressure is 0.625. And then at 1560 CFM, I have a half an inch of static pressure and 0.8 inches of total pressure. This would be what's called the fan characteristic. And that all would be at a constant RPM speed. Now, it's not entirely constant. I mean, I tried to find on the chart the values that landed closest to 1096 RPM. But that kind of gives you an idea of how the fan operates. Okay? So, that's about it in terms of fans. We could go further, but I just kind of wanted to keep it basic for now. So basically, you're looking at fans. You have affinity laws for the fans, and then you also have how the fan operates in terms of static pressure, velocity pressure, and total pressure. Now, fans are what produce pressure. The ductwork the duct system is obviously what takes pressure away from the system. So what we're going to do now is look at look how to size, basically how to size in all air systems. So again, before we get started, I just want to mention that head loss through air systems is all measured in inches of water. So head loss through air duct systems is measured in inches of water. Again, the reasoning behind that is just because the pressure is really low, but they kept it in terms of head. Okay, two methods we're going to look at. One is called the equivalent loss method, or the equivalent length method. This basically is telling us that the total loss is going to be the actual tape measure length of the duct plus the fitting equivalent lengths all multiplied by pressure per equivalent length. So the way that that translates is the following. Delta H is going to be, the problem statements are going to give you the length of the duct. So I'll call that problem given. So you have the length of the pipe plus table 1214. Table 1214 in your book is a table that gives you the equivalent lengths of various fittings. Now, for the context of the class, we're going to stick to all the fittings that that particular table has. So again, that would be table 1214. Just so you know, that's on page 435. So you're going to look at that and then multiply the sum total of that by the losses given in figures 1221 and 1222. So I'm just turning here in my book right now to give you an idea of where those figures are found. Figure 1221 and 1222 are given on pages 420 to 421. And I'll go over a little bit of what that looks like. Okay, so that will be the equivalent length method. The next one is called the loss coefficient method. Okay, so the loss coefficient method is, first it looks at the actual duct length multiplied by the pressure per length. Okay, that is almost the same as the equivalent loss method, with the exception of the fact that you're not actually using any sort of fittings. You're just looking at the tape measure length and then getting the head loss associated with that. And then after that, you add to it the coefficient associated with a certain fitting multiplied by the velocity pressure. So the way that translates into is going to be, delta H is going to be, again, the lengths given in the problem multiplied by the losses that you find in figure 1221 and 1222. And I'll go over what these figures look like in a minute. And then what you're going to do is that you're going to add the coefficients listed in tables 12.8 through 12.12. That multiplied by velocity pressure. Okay? Now, normally when we're in class, what I would be doing right now is having you guys take your books out and opening the books to a particular page to look at those charts. I'd like to do that a little bit right now with you and to see if it works. So let's first look. I'm going to go back a slide here, and I'm going to look at the equivalent length method. I'm going to explain it again orally. So now I'm going to pretty much leave this slide up, and I'm going to talk you through the chart. So go ahead, excuse me, go ahead and take your book and open it up to page 435. So I'm doing that as I talk. On page 435, you should see You should see a table, table 1214. It's titled "Approximate Equivalent Lengths for Selected Fittings in Circular Ducts." The first column, called fitting, is what it is. I mean, they're just five different groups of fittings. You have elbows, transitions, entrances, branch fittings, and then diverging branch fittings and converging branch fittings. So I'm going to go ahead and open this to a blank slide just to illustrate what they look like. I mean, elbows, you guys should know what elbows look like. They kind of have this, right? This look. You have air flowing, and it's just an elbow. The elbows can be at several different angles. You can have here a 90-degree angle. You can have an elbow at a 45-degree angle. So you can have elbows at several different angles. The next one, abrupt transitions, is just what it is. It's basically transitioning from one, how would I explain it? Transitioning from round to rectangular boots or abrupt expansion. So basically here you have, like, for example, converging, like, we're not going to be dealing much with transitions in this class, but basically you have transitions going from one duct to another, but we're not going to deal with that as much. The next one, looking at entrances, you have sort of like a plenum. Let's say you have here your air supply coming in, and it's being pushed into a duct of a certain diameter. Again, all these, just so you know, all these ducts are for round ducts. So this is all for round duct work. Table 1214. We're not going to deal with square ducts in this class. We're going to deal mainly with round ducts. So entrances would be, for example, this would be what's called a 90-degree abrupt entrance. So you have air coming into an abrupt entrance here. Next one, branch fittings. Basically, if you have flow coming and they diverge, this would be diverging at a 45-degree angle. Here's a T-branch, diverging that way with the flow being split. Excuse me, sorry. And then converging would be the opposite. You would have, here would be a 90-degree T converging, where flow merges, 45-degree merging, and so forth and so on. All right, I'm going to go ahead and erase that. I'm going to go back a few slides. So that would be the first column of table 1214. The second column, actually, you know what? I was going to leave this on this slide. Sorry, this seems kind of choppy. I'm kind of making sure I keep this all in one video, so I'm going to be hem-hawing a few times here and there. The next column is labeled L over D. So the first column is fittings. The second column have numbers, so it starts with pleated elbows at 15, L over D 9, 6, so forth and so on. What that is, this represents the length of a pipe per diameter. I mean, so that's literally length. So if I have a length of 10 feet, and my diameter is 1/4 of a foot or 3 inches, yeah, 1/4 of a foot, I would divide that math out and I would get an equivalent length of 40. So what that basically is, it's my length over diameter. So if you look at the top here, it gives you equivalent length. Sorry, let me erase this. So if you look back at the chart, the top part of the chart gives you equivalent length in feet, and then in parentheses it's the diameter. All right, so here, sorry, I'm not making much sense. So here's L over D, and then the next column is, here we have 6 inches or 15 centimeters, then 8 inches diameter is 20 centimeters. So here's your fitting. Here's the equivalent length, and then the next step over would be basically the diameter of each individual. That would be the diameter of the ductwork, and that would be the diameter of a 8-inch ductwork, 6-inch ductwork, 10-inch, and 12 inches. Okay, so those are all different diameter ducts. As you come below, you're going to find the approximate equivalent length associated with the loss. So the equivalent length would be, for example, if you're looking at a pleated elbow. So here's man, my writing's really bad. I'm sorry, guys. For a pleated elbow at 10 inches, that would give you an equivalent length of 13 feet or 4 meters. Okay, so it would be the equivalent length at the associated diameter. Sorry, I don't know why that took so long for me to explain. I think I was looking at the chart and trying to talk at the same time and it wasn't working out. So if I have a pleated elbow at a 90-degree angle, that's what the first entry is, and I have a 10-inch duct, I would have the equivalent length of 13 feet. Okay, and that's basically how it is. So what I would do is come back, I would take the actual length given in the problem. Sorry, that's loss coefficient method. I would get the actual length in the problem given plus the equivalent length, and once I get all those together, I would multiply it by my pressure drop per length, or per 100 my pressure drop per length. How do I get the pressure drop per length? Let's go ahead and turn to page 420. Page 420 and 421. 420 and 421 give you charts that allow you to figure out what your loss is in terms of inches of water per 100 feet of ductwork length. Figure 1221 is meant for galvanized. They're both for galvanized steel, but 1221 is for English units, and 1222 is for SI units. Okay, so we're going to go ahead and look, for example, in figure 1221. So on the y-axis, you get loss per 100 feet, and again, the loss is in inches of water, and the x-axis is flow in CFM. And then much like for the piping networks, you have here on one diagonal you have your ductwork diameter. So this would be diameter. So if I start here, I think the smallest diameter on the upper left-hand side is 3, then the next one is 4 inches, then 5 inches, 6 inches, so forth and so on. Okay, so I'm going to go ahead and erase that. Going the other way, this diagonal, you will find velocity. So if you look all the way to the bottom left-hand side, you should see 300 feet per minute, 400 feet per minute, 500 feet per minute, so forth and so on. What you're basically going to do is pick the diameter. You're going to pick a diameter ductwork so that you stay within the pressure limits of the fan supplied. I'll go over a little bit more about how that works, but basically you would pick a certain diameter associated with a certain flow, and that would give you the corresponding loss per 100 feet. The best way to go about this is with an example problem. So we're gonna go ahead and launch into that. So let's start an example problem here. Thanks for bearing with me, guys. I kind of got myself a little started mumbling a lot for looking at the table 1214. So I hope that didn't confuse you too much. Even if you are confused at this point, this example problem should help clear it up. So let's look at it. It says compute the loss in total pressure for each run of the duct system shown in the figure below. The ducts are of round cross section. Turns and fittings are shown. Use the loss coefficient and the equivalent length approach. So we're going to do both. I'm just going to start with the equivalent length method, and then I'll go ahead and explain the loss coefficient method, and we'll do it that way. So again, here I have a plenum. It's supplying air to this duct system. This length from the plenum to here is 25 feet, and it gives me the duct size of 12 inches. Then I have 10 feet rise, then 20 feet to this point right here. This splits to a 10-inch duct going down, and then this keeps at 12 inches all the way to the end. All right, this branch here is at 300 CFM. This branch here is at 500 CFM, which means that this branch here should be at 800 CFM. So I'm going to go ahead to the next slide, and I'm going to redraw this and section off each of the sections. So here's my plenum with air coming in. I have a split here, and then it continues. I'm going to call this section 1, section 2, and section 3. Section 1 is 800 CFM at 12-inch ducts. This is 300 CFM at 10-inch duct, and this is 500 CFM with a 12-inch duct. Right now we're going to go ahead and size this according to the equivalent length method. So I'm going to make a table. I'm going to make a table by dividing out the table in terms of the I'm going to make each column within the table. I'm going to have columns that are associated with each fitting. So I'm going to go ahead and start with a section Then I'll put in my diameter. My diameter is in inches. Then the length in feet, the length of the total section. Then flow rate in CFM. So let me go ahead and start there. Section 1, Section 2, Section 3. Section 1, it gives me 12 inches. Section pipe duct size. Size 2, Section 2 is 12 inches, and Section 3 is 10 inches. Total length. If I go back and add for Section 1, the length here, here, and here, I should have a total of 55 feet. And for Section 2, it should be 72 feet. And for Section 3, it should be 20 feet. My flow rates, 800 CFM, 500 CFM, 300 CFM. Okay? Now I'm going to make another column to illustrate all of the different fittings we have. So I have an entrance, which is only associated with Section 1. Then I have elbows. Looks like each section has an elbow. I have 2 here in Section 1, 1 here in Section 2, 3, I'm sorry, and 2 in Section 2. Branches. I have branches for Section 2 and 3 and not 1, and I'll go over that in a minute. First, let's looking at the entrance. Here I have an abrupt entrance into a 12-inch duct. So if you guys turn back to table 1214, all right, let's look at table 1214. I have a branch fitting. I'm sorry, not branch fitting, I'm sorry, an entrance, an abrupt entrance. This abrupt entrance is for a 12-inch duct. So you should find an equivalent length of 30 feet. Again, 12 inches, if you look at the table 1214, abrupt entrance is the first entry underneath entrances, and then 12 inches is the largest diameter on the chart, so that's all the way on the right hand side. You should see an equivalent length of 30 feet. For the elbows, if we go up to the top, we can look at the associated elbows that we have. Oops, sorry. When I say top, I mean the top of page, the top of the chart. So page 435. If you look at pleated elbows, all right, we'll assume pleated elbows. How do we assume pleated elbows? I'm telling you, it's pleated elbows. For section number 1 at a 12-inch duct, you should find for a 90-degree pleated elbow, because if you look at section 1 here, these are 90-degree elbows. You should find that it is 15 feet. So if you look under 12 inches, we have 15 feet. So this would be 2 elbows, each at 15 feet. And it would be the same thing for section 2, because section 2 also is 12 inches. So that would be 2 elbows at 15 feet. Equivalent length. Now for section 3 now we have a what looks like a 45-degree elbow at 10 inches. So 45-degree elbow, this would be a pleated 45-degree elbow. So if you go to your table and find that for 10 inches, you should see an equivalent length of about 8 feet. Again, pleated elbow, 45 degrees at 10 inches should give you 8 feet. Okay, now concerning branches, what are branches again? Branches are where you either have a merging or a diverging of air. So this would be considered a branch right here. We have air flowing and it splits up in two ways there. How do you deal with it? Whoops. Let me redraw that real quick. The way that it's dealt with is that you're going to include the loss of the branch in the section that they're branching to. So for example, since this is flowing this way and this is being diverged into this section and this section, I'm going to count the loss of the branch on the sections that we're diverging to. So this will be a loss for sections 2 and 3, since it's diverging to sections 2 and 3. So for example, there would be no branch loss for section 1 because this is branching into section 2 and section 3. If it was going to be a converging, I would go ahead and include it in the section at which it's going to. Okay? So, let's go ahead and do the branch for section 2. Section 2, we have 12 inches, and we have basically, it looks like a Y branch, right? So if we look at our branch this way, this is probably at about a 45-degree angle. And there's two sections. There's the through, which would be section 2. And then there would be the branch. So what we're going to look at is a through loss for section 2 for 12 inches. So if you go to your table and you look under branch fittings, diverging, the first entry is for a Y branch at 45 degrees. The first entry is for the branch, and then the second entry is for the through. Section 2 is a through because it's just going through at 12 inches. So if you look at it, that's the second entry in there. If you look all the way over to the right, you should see a total loss of 8, or an equivalent length of 8 feet. Again, this would be for the through branch. If you look under branch fittings on the chart, you should see branch fittings. I wish I had actually put it on the presentation, so since I don't have a presentation, I'm just going to have to explain it. You should see Y, 45-degree branch, and then the second entry is the same thing for through. This is what you're looking at as the through branch. If you look all the way for 12 inches, you should see a total loss of an equivalent length of 8 feet. So go ahead and fill that in. And now for section 3, we have 10 inches, right? So we have a 10 inches, and it is a branch. So the branch should be, sorry, I hesitated for a second because I was looking back on the chart to make sure I had the right numbers. You should see for 10-inch duct for a Y 45-degree branch, diverging branch fitting, you should see an equivalent length of 17 feet. Okay? So that would be all of our fittings: entrance, elbow, and branch. I hope that was clear, guys. I know that I've been hesitating a little bit. This video is not the best choice. I definitely will go over this a little bit more in class when I get back next week. Okay, so anyway, what we're doing now is that we're going to add up our equivalent length. So we take the 55 feet of tape measure length, add 30 feet for entrance for section 1, and then add another 2 times 15 feet for the elbow. We should get a total equivalent length of 115 feet for section 1. If we continue that, 110 feet for section 2, and 45 feet for section 3. Okay? There's our equivalent length. So now, what we're going to do now is that we're going to go ahead and we're going to find what our pressure loss is per 100 feet. So let's look at the pressure loss per 100 feet. Let's go to table. What units are we working with here? We're working with English units. So let's turn back to page 420. You should be able to look at the table or figure 1221 on page 420. Let's go ahead, for example, and take for a flow rate of 800 CFM and a diameter of 12 inches. So if you look at your chart, you should see on the y-axis your friction loss in terms of loss per 100 feet, and then flow rate on the x-axis. Find, for this example, 800 feet, 800 CFM. All right, so let's say it's right there. You go up the chart until you intersect 12-inch duct. All right, so go ahead and try to find 12-inch duct. Once you find an intersecting point, go over and find the loss. You should see in this case a loss of 0.135 inches of water per 100 feet of duct length. Right, so then you do the same thing for 500 CFM, and you would find a lesser loss, right? 500 CFM for section 2 at 12 inches, you should find a loss of 0.061 inches of water per 100 feet of duct length. And then for section 3 at 10 inches for 300 CFM, you should find 0.023. Sorry, 0.0, I messed up those last two. For section 2, you should find 0.055. My apologies. 0.055 inches of water per 100 feet of duct length, and then 0.053 for section 3. That would give you a total loss. So if you go ahead and take 115 feet, and then you do the math for 0.135 inches of water loss per 100 feet, you should get a total of 0.15 inches of water for the loss of section 1, 0.061 for section 2, and 0.023 for section 3. Okay, guys, I hope this is clear. Again, I know this video isn't quite the optimal way to teach this stuff, but this should give you a pretty good idea. Now, just to make sure everyone's on the same page, I'll go ahead and label where you should be seeing all this. So, table 1214, page 435, you would basically get, for table 1214, you would get the losses at specific diameters and fitting types. So you get the fitting type, you get the diameter, you should get an equivalent length for all these fittings. And then figure 1221 on page 420, you can get the loss per 100 feet. You can basically get your loss per 100 feet for flow rates at specific diameters. This would be the equivalent length method. Okay? I hope that's clear, guys. The next thing I want to look at would be the same problem for the loss coefficient method. Now, the loss coefficient method is a little bit different. I'm going to split this up into two things. If you look back into the prior slide where we went over this. The loss coefficient method basically looks at your loss associated with the actual duct length. So that's almost similar to the equivalent loss method. You take the loss associated with a certain duct length, and then what you do is that you add the loss due to all the fittings. Okay, so I'm going to cover this problem in two ways. We're going to look at basically looking at the loss associated with just the duct length, and then we're going to look at the losses due to all the fittings. The fittings losses are associated with several different tables, and those tables start on page 426, and they go through page 432. All the tables do is give you a coefficient, and what you do is that you just add all the coefficients together and then multiply it by the velocity pressure. All right, so the best way to do this is just by example, especially given the fact that we have this, the fact that I'm doing this by video. So let me split this up. Let me go ahead and start making a table again here. We have section, diameter, length, loss per 100 feet, and then total pressure. So that would be what I'm going to do first. I'm going to go ahead and for each section I'm going to list the diameter in inches like we did before, the actual tape measure length in feet, and then what I'm going to do is get the equivalent loss per 100 feet. This would be like what we did in the prior, for this problem in the equivalent loss method. So if I go ahead, according to figure 1221, I can go ahead and pull the same losses, or the same loss per 100 feet as I did in the prior slide. So that would be knowing the diameter, knowing the flow rate. I can get these from figure 1221 at specific diameters and flow rates. And then from there, knowing my loss, knowing my length and knowing the loss, I can find what my actual pressure loss is just for the length of pipe, not counting the fittings. Okay? Again, this is the loss associated with length, not including the fittings. Now, what I'm going to do now is go ahead and using tables 12.8 through table 12.12, we're going to find the coefficients associated with each fitting. So let me go ahead and let's start with an elbow. Okay, we're going to need to know certain parameters ahead of time. So we're going to need to know flow rate. So I'll just list those again: 800 CFM for section 1, 500 CFM for section 2, 300 CFM for section 3. Next thing we're going to have to know at some point is also our flow ratio. What do I mean by flow ratio? I mean the flow of a certain section the flow of the section in question to the flow of the flow of the section prior. So for example, if we're looking at section 1, there is no section prior to that, so that would be basically be 1, 800 over 800, which would be 1. For section 2, section 1 is flowing into section 2. So that would basically be 0.3. Sorry, this would be 0.3, 3/8. It would be 3/8 for section 3, right? Because we have 300. I'm just pulling out my calculator real quick as we speak right now to confirm the numbers that I have. So if we're looking in those terms, I would have, sorry guys, bear with me here. 0.38, right? So because it would be 300 over 800. So the fact that section 1 is flowing into section 3, that would be 0.38. And then for section 2, it would be 0.625. And here we have area over area would be the next column we're looking at. What's that mean? The area of the section in question to the area of the section that's flowing into it. So it would just be 1 for section 1. Section 2 and section 1 have the same diameter, so it would be 1 as well. Section 3 has an area, has 10 inches. Section 1 is 12 inches. Section 1 flows into section 3, so the ratio of the areas would basically be the ratio of the square of the radiuses, so you would end up with 0.7 in that case. Okay, why did I just do that? Those are some parameters that we're going to need for certain tables. Let's look first at entrances. Again, no entrances for section 2 or section 3, because if you go back to the problem, you should see that section 1 has an entrance. So, with that said, for section 1, let's look at the entrance coefficient. That would be associated with table, as I'm looking through this, I'm trying to find the table associated with entrances. So that would be table 1210. So table 1210, page 428. If you look at it, you're going to find entrances for different angles. So here in table 1210, you're going to see a diagram, and the diagram is going to have on it coefficients associated with this angle theta. This angle theta that's made in this entrance. Since we're dealing with an abrupt entrance, you know, we have an angle theta of 180 degrees. So you get these different coefficients as a function of, you have one column all the way to the left, which is L over D. That column is basically the length here of this section right here. That would be L, divided by the diameter, right? That's what this is. And then there's different columns for theta. You have starting with theta equals 0, 10 degrees, 20 degrees, so forth and so on. So I'm going to go ahead and erase all that. So what we're dealing with is 180 degrees. So if you look all the way to the right, for 180 degrees on that table, you should see 0.5 listed for each corresponding L over D. It should still be 0.5. So basically, since we don't have to worry about the type of entrance it is in terms of the length of the entrance, because it's at 180 degrees. So our coefficient then is going to be 0.5. The next one we're going to look at is elbows. Each one has an elbow. What I mean is that each section has an elbow. So that would be table 12.8. So that's table 12.8, page 426. The elbows are going to be listed in terms of, all the way to the left you have angle. So there's three angles they list: 90-degree elbow, 60-degree elbow, 45-degree elbow. And then there's going to be different columns for different diameters. So you have 4-inch diameter duct, 6-inch, 8-inch, so forth and so on. 10 and 12. So for sections 1 and 2, for sections 1 and 2, both of them have two 90-degree elbows for 12 inches. So here's 90 degrees, 12 inches. You should see a coefficient of 0.26. So you should have here 2 times 0.26. 2 times 0.26. Now, for section 3, it's 10 inches, and we have a 45-degree elbow. So you should find that intersecting point here, which should be not 0.45, sorry, 0.17. So here you should have 0.17 as your coefficient. So I'm going to go ahead and erase this right now. Okay, and then finally the last section, which is the branch. We have no branch for section 1, but section 1 branch diverges into section 2 and section 3. So for diverging branches, you should use table. Well, there's two tables for diverging branches. One is table 1211, and then table, well, there is one table for diverging branches. So table 1211, and there's two parts to it, A and B. A is for a diverging 45-degree branch. B is for a 90-degree diverging branch. So here, this would be table 1211A, page 429. So for section 2, it's a through. This is where we're going to need these two parameters, this Q over Q and A over A. So if you look, if you look, let me rewrite that here, method, since I erased it. If you look at section 2, it's a through branch. So there's two here. You should see two sections here. You should see one named branch and then a table. And then underneath it is main and then a table. So we're going to go look for section 2 would be a main, since it basically is going from section 1 to section 2. It's going through. So you're going to look at the main. The first column is A over A. So you have different values starting at 0.1 going down to 0.9. So here you're going to probably use the 0.9 row, since this is the closest to 1 we have. And then there's several Q over Qs. Basically the flow rate of the section you're analyzing divided by the flow rate that is flowing from. Starts with 0.1, then 0.2, all the way down to 0.8. We're looking at 0.625, so 0.6 would be the column we're looking at. So if you look at 0.9 for the area of section 2 divided by the area of section 1, which is as close to 1 as you can get. And then you have the flow rate of section 2 divided by the flow rate of section 1 is 0.6. You should find that coefficient to be 0.16. And then basically you do the same thing for section 3. Let me go ahead and finish erasing this. Okay, for section 3, it's a branch. So if you look at A over A, you should find for 0.7, For the Q over Q, in that case, it's about 0.4. You should find the intersecting point at about 1.57. Okay? So we just finished doing all of the coefficients. And then you would get a total associated pressure. The way you calculate it is, you have total pressure is going to be your length multiplied by the pressure per length per, so that would be this part, plus the sum of all the coefficients for a particular section multiplied by the velocity pressure, V over 4,005 squared. So if we do it, for example, for section 1, we get 55 feet, right, is the length of section 1 times the loss, 0.135 inches of water per 100 feet of length, plus the sum of all the coefficients, 0.5 for the entrance, and then there's 2 elbows, multiplied by the velocity. You guys can go ahead and calculate the velocity, okay? So in this case, if you were to calculate the velocity for section 1, you should get 1,030 feet per minute divided by 4,005 squared. You get the total pressure to be 0.141 inches of water. So if you go ahead and do that, you should be able to fill in all the blanks. The only thing on this chart that I didn't include is the velocity. And there's going to be a different velocity associated with each section. You just have to go back and calculate that in terms of using the area. Okay? So that is how you size or figure out the loss associated with each section. Now, in your homework, you're going to end up needing to size some ducts. And the way that you size the ducts is that you just basically have to size the duct system. If you're given a network, right? If you're given a network, you need to be able to pick. You need to be able to pick the size duct the diameter duct for each section of your network, so that the total pressure does not exceed what's available by the fan. In this case, we're not limiting flow like we did for piping networks in terms of pressure drop flow, limited pressure drop because of any sort of noise. This is in terms of what's available by the fan. Okay? All right, one last part to this chapter. I know this is really long. I'm hoping that you guys are stopping this video along the way, because this can be very long if you don't. The last thing we're going to look at is I just want to look at an example here in terms of looking at the different entrances. So here's the example problem. What is the loss pressure for an 18 by 18 duct discharging into a large plenum? The flow rate is 4,500 CFM, and the duct expansion is an area ratio, so the area going out divided by the area in is 4. Assume an abrupt entrance and assume a 20-degree transition. So again, this is using table 12.9b on page 427. So I want you guys to turn to your books, page 427, table 12.9b. That's a transition from one size duct to another. So section A is asking us to find the pressure loss. So that would be the coefficient that we get times the velocity pressure. We have an area expansion of 4 and an abrupt entrance of 180 degrees. According to the table, you should find a coefficient of 10.56. Take a second to make sure you can find that. Whoops. Therefore, your total pressure should be the coefficient multiplied by the velocity divided by 4,005 squared. What's the velocity? Velocity would just be flow divided by area. Again, we're looking at the area we're going into. So in that case, it would be 4,500 CFM over the area. Again, in square feet. So if we get about 500 CFM, sorry, not CFM, 500 feet per minute. Should get a pressure of 0.165 inches of water. Okay. What happens if you increase the angle? It's not abrupt entrance anymore, and instead we have an angle entrance of 20 degrees. It changes the problem a little bit. So now we have the same expansion ratio, but now instead we have a 20-degree transition. Well, you should find a smaller coefficient, and basically that smaller coefficient is going to equate to a lesser pressure loss. Okay? All right. That's it for equivalent length. We have one more part of this chapter to cover, and I think what I'm going to do is basically wait until after break to cover that part of the chapter, namely because this video was already long, but you should at this point have enough to finish all, if not most, of the homework. Okay, so we're going to finish off the last part when you guys get back from break. So thanks again for listening through this. I know it was long. I guess I'll see you on Friday for your exam.